conversation about probability, I just want to briefly mention a couple of misconceptions there are about probability. And these might seem silly to you, that people might think some of the things that I'll say, but I think they come up a lot more often than we really give them credit for. So let's jump into it. So let's consider this question. I have a coin and I flip it 5 times and I get 5 heads. Okay, and that's actually pretty unlikely. It's not impossible. I'm sure if you flipped enough coins enough times, you could get 5 heads in a row. But the question is, if that happens, if I get 5 heads in a row, what's the probability that if I flip the coin one more time, a 6th time, that it'll come up with heads? Now, I don't know. You can think about it. Maybe try to give an answer right off the top of your head, what you think the answer will be. But what I want to suggest is that a lot of people, and maybe particularly younger kids that are new to the idea of probability and haven't really thought about this carefully, might be tempted to say that the probability is pretty low. Okay, it might only be 10% or 20%. Because there's been so many heads, there have been 5 heads in a row, it has to be the case that it's more likely to get a tails, to level things out, or something like that. But that's actually incorrect. So let me tell you the answer. The answer is actually really simple. It's 1/2. Even though we've had all this past information about getting 5 heads in a row, every time I flip a coin, the outcomes are independent of any other flip. Okay, so that means that in that 6th flip, there are exactly 2 outcomes in my sample space, heads or tails, and they're equally likely. So the probability is still 1/2 that it would be heads. And now some of you may be thinking, well, why would you think that? Why would you think that the past information would make a difference? Maybe you sort of believed that maybe it might. This is actually kind of a famous probabilistic fallacy. It's called the gambler's fallacy, and it loses people a lot of money. So you go to a casino and you notice a trend and you say, okay, well, this trend cannot continue. There's something going on behind the scenes where things need to level out, right? If I get 5 heads in a row, I have to get the tails next time to balance things out. But that's actually incorrect. So this really gets at the notion of something we're going to talk about later, which is independent experiments versus dependent experiments, and when outcomes are independent as opposed to when outcomes are dependent. So the important thing to note here is that flipping a coin, every time I flip a coin, the outcomes are independent. It does not matter how many times in a row I flip heads. The next flip, there's still a 50-50 chance of getting a head or a tail. Okay, so here's another question that some common misconceptions come up about. So let's say I flip a coin 6 times. And the question is, how many heads am I going to get? Now, if you think about it, and maybe if you sort of have been tracking with our conversation about probability, you should know that the correct answer is that it depends. Sometimes you might get 3 heads, sometimes you might get 4 heads, sometimes you might get 6 heads, sometimes you might get 0 heads. It really depends, right? There's variation in the outcomes that you can get. So what's the misconception here? Well, maybe it's not so hard to misconceive when there's 6 flips, but what if instead I changed 6 here? What if I changed this to 10,000 flips? I flip a coin 10,000 times. How many heads will I get? Well, again, the correct answer is that it depends. But the fallacy here that comes up, and this is very common with students, is that if you put a big number here, people will start to believe that there should be exactly half of the flips coming up heads. So, if I flip a coin 6 times, there should be 3 heads. Or if I flip a coin 10,000 times, there should be 5,000 heads. And it's just this way of thinking where, okay, there's a 50-50 chance. So if I flip it enough times, half of them will be heads and half of them will be tails. But that's not exactly how it works. Okay, so really, you could still have any number of heads. If I flip a coin 10,000 times, I could still theoretically have 0 heads, or 10,000 heads, or 1 heads, or 563 heads. Doesn't really matter. But let's actually redefine the question here and kind of get back into something we talked about before, which is the binomial theorem, which is really helpful in looking at these sort of situations. So what if I change the question to, instead of I flip a coin 6 times, how many heads will I get? Let me ask this question. What is the probability of flipping exactly 3 heads? Okay, so you see the difference here. And this is the right sort of question you should be asking in these probabilistic experiments. You should never ask, if I do this random experiment, what will the outcome be? I don't know. Well, because there's going to be more than one outcome, right? So we really need to think about what is the probability? How many of the outcomes are favorable to the event we're interested in? And so how do we answer this question? Well, if you remember our discussion on the binomial theorem, we can sort of model flipping a coin 6 times in the following way. So I can put a H and a T and then raise that to the 6th power. And now by the binomial theorem, if I look at Pascal's triangle, the 6th row, I should have something like 1 times h to the 6th plus, 6 times h to the 5th times t. Okay, and again, if you're not tracking with me, all I'm doing is I'm multiplying h plus t times h plus t times h plus t times h plus t 6 times and doing this foiling process. Okay, you can do that, but a shortcut is to look at Pascal's triangle. So the 6th row of Pascal's triangle will give you the coefficients of the terms in this expansion. And so if I keep going, so we have 1, we have 6, the next one will be, 1, 5, 10, so 15. And that'll be h to the 4th times t squared. Notice what I'm doing is I'm just decreasing the exponent of h by 1 each time and increasing the exponent of t each time. Here you can think about there's a t to the 0 term. Okay, so we have 1, 5, 10. Okay, and then 20 times h to the 3rd times t to the 3rd. Okay, so I'm just going down Pascal's triangle. There's going to be some symmetry going on. So we'll go back to 15. And this time it'll be h to the 2nd, t to the 4th, and then 6 h to the 1st, t to the 5th, and then the last term will just be 1 times t to the 6th. Okay, so the interpretation here is that if I flip a coin 6 times, there's one way to get 6 heads. There are 6 ways to get 5 heads. There are 15 ways to get 4 heads. There are 20 ways to get 3 heads. There are 15 ways to get 2 heads, 6 ways to get 1 head, and then 1 way to get 0 heads. Okay, so it's just breaking down the sample space into these various events. So the probability is going to be, so 6 heads, no, not 6 heads, 3 heads. Flipping a coin 6 times, getting 3 heads. Well, the favorable outcomes, there are 20 of them. So we have 20. And then what about the total number of outcomes? Well, there are 2 to the 6, so remember that I just multiply. Each one of the coin flips has 2 outcomes, so I have 2, and then I have times 2 more, and then I do that 6 times, so that's going to be 2 to the 6, which is 64. So the probability is 20 over 64, and I can give that as a percentage. So that's 31.25%. But this is interesting. So this is saying that if I flip a coin 6 times, what's the probability that I get 3 heads, which is probably what I would expect? It's actually pretty low. It's less than a third of the time am I going to get exactly 3 heads. But what we can verify is that this is the most likely outcome. So if I look at the probability of getting 4 heads or 5 heads or 6 heads, all of those probabilities are going to be smaller than getting 3 heads. So sometimes you'll say that this is like the expectation that you would get 3 heads. So if someone comes up to you and says you are going to get 3 heads, that's not correct. But if they say you're most likely to get 3 heads, that is correct. That's more in that probabilistic language rather than an absolute. And that's really what probability is about. What's the most likely outcome? What could I expect to happen? Okay, so here's a graph that's looking at flipping a coin 6 times. So we'll let this capital N be the number of flips. So this is 6. And this is the distribution of the number of times amounts of heads can occur. So we see that 3 heads occurs 20, 2, 15, 1, 6, and 0, 1. This is exactly that Pascal's triangle we looked at before. So we have 1, 6, 15, 20, 15, 6, 1. Okay. But you see, if you're just thinking about, okay, I flip a coin 6 times, what can I sort of expect to happen? Now, the most likely event is that we get 3 heads. Okay, so you see that's the highest number of outcomes, so it's going to give us the highest probability. But if I sort of truncate maybe here and here, I can say something a little bit stronger, that the majority of flips I'm going to get between 2 and 4 heads. It seems to be pretty unlikely that I'm going to get 0, 1, or 5 or 6. Those are going to be sort of the outlier when I flip. Okay, but what we can do is we can increase the number of flips and see what happens to this graph. Okay, and this is where, even though you're never going to be able to guarantee you're going to have half of the flips come up heads, what you are going to see is a narrowing of this graph. So what I mean by that is that where the majority of the number of heads are going to lie are going to narrow in around about half. Okay, so let's look at the next graph. Okay, so here we bumped up to n equals 10. So this is looking at what happens if I flip a coin 10 times. Here's the number of ways I can get 0 heads, 1 head, 2 head, 3 head, 4 head, 5 head, etc. And as you'd expect, the most number of outcomes are 5 heads. So the most likely outcome if I flip 10 coins, it's going to be 5 heads. But you can already start to see that it's becoming a lot less likely to have 0 heads or 10 heads or even 1 or 9 heads. It really seems like most of the flips are coming in here. So I'm sort of narrowing in. So if I flip a coin 10 times, I expect the number of flips to be pretty close to 5. Now, it's not always going to be 5, but it's more likely to be close to 5 in some sense. And you can sort of quantify this. Actually, in my notes, I write out a proof using just some really simple calculus. What exactly I mean by this, I mean the relative width of this distribution is going to 0 as n goes to infinity. Okay, you don't need to worry about that. But let's jump up to n equals, say, 100. I think let's look at n equals 20 first, and then n equals 100. And so you can really start to see this narrowing I'm talking about. So here's n equals 20. So I flip a coin 20 times. And here's the distribution of the number of heads. And now you see, look at 0, 1, 2, or 3 flips, and then 17, 18, 19, 20 flips. Those are basically never happening. I mean, it is possible. You could look at Pascal's triangle, the 20th row, and see exactly what these values are. You know, this will be 1, and this will be 1, and then so on. But relative to the number of times I can get 10 heads, I'm basically never going to get 0 heads or 1 heads or 2 heads. Again, it's looking like most of the data is sort of squeezing in around 10 flips. So half of the time, the number of heads is going to be pretty close to 10. And when we go up to n equals 100, this will be even more pronounced. So let's look at n equals 100. So now we're really starting to see this very pronounced normal distribution with a standard deviation that's getting really small. Okay, that's just another way to say what I've been saying. If I flip a coin 100 times, almost none of the time am I going to get between 0 and, even 35 flips, and then here 65 to 100 flips. That's basically never going to happen. I mean, it can happen. It is not impossible for it to happen. It's just extremely unlikely. It's most likely, if I flip a coin 100 times, to be pretty close to 50. I mean, it would be unexpected to get, even below 40 or more than 60 heads if I flip a coin 100 times. So again, you're just seeing this narrowing of the distribution. So it is true, like I said, that if I flip a coin a bunch of times, 1,000,000 times, 1,000,000,000 times, I can expect with pretty high likelihood that the number of flips is going to be very close to half coming up heads. Now, it's not necessarily likely that I'm going to get exactly half heads, but it will be closer and closer to half as I flip the coin more and more times.